summer I was working at this desk, which is where I was a lot of times talking to people as they came in. I was kind of looking down, and all of a sudden I heard a voice from the heavens, or it could have been from the heavens. But it was a voice I recognized, but I couldn't place the person where I heard it from. And then, of course, I knew that voice because I'm an NCPR listener. And struck up a conversation with Aileen A, and it was just a great conversation, and we talked about her possibly coming here and being part of this lecture. At that point, it was like very much kind of just an e-thought. But so happy to have her here tonight. So from St. Lawrence University, Dr. Aileen A.
All right, so what I want to talk about tonight is the large-scale structure of the universe, and it's something that we're learning more and more about, really in very recent times. So this is some of the newer stuff. So let's start with galaxies. So galaxies in the large scale is how I think this was advertised. So galaxies were first discovered as these spiral nebulae, they called them. And they didn't know if they were within our galaxy or different galaxies themselves. And this is our neighboring galaxy, the Andromeda galaxy, that's actually, we're falling toward it, or we're falling toward each other, and should collide in a couple of billion years. So Andromeda galaxy, we'll be getting a better and better view of it. But yeah, so we identified these as spiral nebulae. There was a great debate in 1920 between Shapley and Curtis, a couple of hotshot astronomers at the time, discussing the evidence of, are the spiral nebulae within our galaxy, are they outside our galaxy, and how big is the universe? Because at the time, until the 20th century, they really thought the whole universe was just the Milky Way galaxy. And then came a guy, Edwin Hubble, for whom the Hubble Space Telescope is named, and he actually first measured distances to galaxies, and he did it by measuring variable stars. These Cepheid variable stars, and I'll show you some images of one on the next slide. It was discovered by Henrietta Swan Leavitt that they vary. The rate of variation is proportional to how intrinsically bright they are. That's how many watts of energy they're pouring out into the universe every minute or every second. And that's the information we need to know. And because if we know the luminosity, how bright a thing actually is, like a 100-watt light bulb. So if I have a bunch of 100-watt light bulbs and they're at different distances, if I know they're 100-watt light bulbs, then I can figure out the distance. Because as this shows, that as you go out, this is actually yesterday's image of the sun. Here's an area, and that area gets bigger as the size of a sphere. And so what gets to us, the amount of light falling on us, is called the flux, and it's the luminosity, how bright the object actually is, divided by 4 pi r squared, where r is the distance to the object. So we can get the distance fairly easily. If we can measure how bright it appears, that's pretty easy. And if we have some way to know how bright it actually is, that will allow us to calculate distance. And so Hubble did this. His first estimates were incorrect. Here again is the Andromeda galaxy, and he measured 900,000 light years. We now know it's about 2.5 million light years away. But that expanded the universe a huge amount when he measured this. And it told us absolutely that these had to be other galaxies. And so the universe became much bigger. And here is, again, the Andromeda. And here is a variable star. Here's December 17th, 2021, or 2010. Here's the 21st of December. Here's the 30th of December. Here's January 26th. and you can see how its brightness varies. Not a huge amount. I mean, these are giant stars in their death throes, and what's happening is that stars are nuclear explosions contained by gravity. And so gravity is always trying to squish the star, and gravity will win. But the nuclear explosion in the center of the star is pushing out against gravity. And they live in this dynamic equilibrium with both of these forces trying to win. And for the sun, it'll live 10 billion years in this state of, we call it hydrodynamic stability, and hydrostatic stability, I guess. But when they go to die, the forces, they just oscillate in size. And you now understand the physics of this, but I'm not going to talk about it. And so that's why these stars vary. So they're big, giant stars in their death throes. So they helped us measure the distances to the galaxies. When the Hubble Space Telescope was first put in space, one of its major missions was to be able to isolate individual stars in other galaxies so we could find these variable stars so that we could determine the distances to other galaxies farther away than the Andromeda. And so it's been very successful in that regard. So the other thing is that the galaxies are not just hanging out there in space, they're moving. And Hubble also did this work. So the Doppler effect, I hope you're all familiar with, it gives how fast an object is moving toward us or away from us. With sound, all right, if it's coming towards you, it raises the pitch. If it's going away, it lowers the pitch. We all know when there's a car race on TV, because how does it sound? Meow, meow, meow. Because the cars coming at you have a higher pitch, going away they have a lower pitch. And so you hear that. In light, if they're going away, they're redder, and if they're coming at us, they're bluer. And so as soon as we look at the spectrum and identify the lines of, say, hydrogen, which is the most abundant element in the universe, we can say how fast it's moving, toward or away from us, because we know the wavelengths of the hydrogen lines really well. So Hubble observed these spectra, again in the 1920s, and so the variable stars gave the distances, the spectra gave the redshifts. He could calculate how fast these galaxies were moving, and with a couple of exceptions, like Andromeda, they're all moving away from us. And those distant ones, more distant ones, are moving away faster. And of course, your first inclination is, do we stink? And the answer is, well, of course we do, but galaxies really don't care. That's not why they're going. So this is his plot from the paper published in 1929. And these were the galaxies that he plotted. And it's, not a perfect fit, but there is definitely a trend. And his data, these were very preliminary data, so it's tightened up quite a bit by now. And so these distances, 10 to the 6 parsecs, a million parsecs, is 3.26 million light years. So the galaxies here, that light had been coming at us for 3.26 million years. So that's how far away the galaxy was when the light left. And so here, these are out at twice that. And then this is how fast they're moving. So you can see, if they're farther away, they're moving faster. This is a wonderful tool for astronomers because now it's really easy to measure their recessional velocity. It's really hard to measure their distance in any other way. So if we can just measure their recessional velocity, we can say it's going this fast, it's this far away. How convenient. But it's still like, why are they moving away and the more distant ones moving away faster? Is there a simple way to explain this other than that humans stink? Yes, we'll use queer Bongo cosmology. Queer Bongo was my beloved dog who walked in off the desert in New Mexico into my dorm room at New Mexico Institute of Mining and Technology, where I was a graduate student, and she instantly knew I was her person. And we were together for 16 years, and I still grieve this little critter, but she can teach us cosmology. So let's pretend that these are meters here. So left QB is a meter to the left, and right QB is 3 meters to the right, and here's middle QB. So let's let all those distances double in 1 second. And so now we can see that QB didn't change size. QB isn't expanding, just the distance between the QBs. And that the left QB to double the distance in 1 second, she had to move 1 meter per second. And then right QB had to move 3 meters per second. So if space is expanding, this instantly explains why all the galaxies are moving away and the more distant ones are moving away faster. It's because the universe is a raisin bread. When you make a raisin bread, you make the dough, you put the raisins in it, and you knead it, and then you set it aside, you cover it in a dish towel, and the little yeasties in there do their work, and they make it rise. None of the raisins expand, but they all get farther away from each other. Not because they're moving through the dough, but because the dough itself is expanding. That's what space is doing. Space itself, between the galaxies, is expanding. Why? Well, that's the $64 million question now. But we don't know why, but we know that this is happening. We have a lot of evidence. So the galaxies, this is a hard thing to think, that the galaxies are not moving through space. They're moving with space, because space is expanding. So, the other motion that we see in the galaxies is that they rotate, spiral galaxies do, and this is showing, it's hard to see the colors here, but this is a spiral galaxy, and there are halo stars that are in these big orbits that are spherically distributed around the center of the galaxy, and there are some orbits in the center that are almost spherical, and then this yellow line, if you can see it, is a star in the disk. So the sun takes 225 million years to go around the Milky Way center. As it does so, it kind of oscillates above and below the plane of the galaxy. So they're moving. Well, hey, if they're moving, then we can use Doppler shift. So the side that's going away from us over here, well, that side is going to have an extra red shift because the galaxy is moving away, and that side is moving away on top of it, so this looks redder, and the galaxy is moving away, but this is moving toward us. And so it's a little bluer. So the image of it, the spectrum of a galaxy spreads out because it's rotating, and we can measure that really easy. Spectroscopy is incredibly accurate. It's an amazing, just an amazing tool. And so, we're going to do physics. Did they warn you? All right, math. All right, math folks, close your eyes. All right, so Newton, all right, clunky old Newton, told us that force equals mass times acceleration. So the gravitational force on the star is the mass of that star times its acceleration. If you're moving in a circle, you have to accelerate toward the center, else you go flying off in a straight line. If I had a ball on a string, I have to keep the string attached. If the string breaks, where does the ball go? So you have to accelerate toward the center to go around in a circle. So gravity is holding the stars to the center of the galaxy. So Newton's law of gravity is the gravitational constant times the mass of the galaxy, the mass of the star, over the square of the star's orbit, and that's equal to the mass times the centripetal acceleration, those of you who've had some physics. And so a few things cancel out here, and so we get this simple little equation for the mass. This is how we measure the mass of Jupiter. Or, any body that has moons, we can measure its mass really easily from Newton's physics. So let's tack that up on a wall. Easy peasy. All right, we can do these calculations. Well, as we looked at the motions of the stars and the galaxies, we expected that, they're orbiting the galaxy's center, there's more matter in the middle, that's where all the glowing stuff is, and so we figured that the orbits ought to be closer, the orbital speeds ought to be somewhat like the orbital speeds of the planet. So here's the orbital speed, here's the distance from the sun, and so let me tell you how long these take to get around the sun, and yes, their orbits are larger, but they're also moving slower. So Mercury comes in, its year is 3 months long. Zip, 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 zip. That's why, every time I'm on the radio, Mercury's in the evening sky, then Mercury's in the morning sky, Mercury's in the evening sky. It just pops back and forth. Venus, it has a year, 60% of Earth's year. And so it's been hanging out in the evening sky now all summer long. Hasn't it been lovely? And so then Earth has 1 Earth year. And then Mars, 1.9, almost 2 years. Jupiter, 12 years. I think of Jupiter as moving 1 constellation of the zodiac per year, except Ophiuchus, but we try not to talk about Ophiuchus. And so Saturn is 30, so I'm 2 on Saturn. Uranus, my mom waited to a uranium year. And Neptune, she didn't make it to a Neptunian year, but All right, so that's what we expected. And it's not what we found. This is what we expected. Here's all the stuff in the galaxy. This is what we expected. These stars should be going slow, like Neptune. This is what we found. Oh my God. Physics doesn't work in galaxies. Well, physicists refuse to accept this, so we say, there's more mass to this galaxy than we're seeing. There's some mass, it's pulling on the stars with its gravitational attraction, but we can't see it. This is a problem. But when you have a problem, you need to name it. So we named it dark matter. Clever. Oh, wrong one. So now our model of galaxies is that here's the Milky Way embedded in this dark matter halo that's much bigger than the galaxy, so that these stars way out here with these fast orbits, that fast orbit is due to all the matter, all the dark matter in which they're embedded. So this is a whole new view of the galaxies, and this view is about 60 years old. So let's look at the universe now. So this is an atlas of the universe. The URLs are down here. You can just Google Atlas of the Universe, because it's cleverly www.atlasoftheuniverse.com. All right, and so this shows the Milky Way with the various spiral arms, and we have a dwarf galaxy south of the galactic plane. And so let's start zooming out. And when we zoom out, we find that the Milky Way, which is sitting in here, is in a cluster of galaxies called the local group. There are some dwarf galaxies kind of hanging around by the Milky Way like remora fish, And so those are pretty close, but then here's the Andromeda galaxy, the pretty one. It's the one that's falling toward us because the local group is bound by gravity. And the Milky Way and Andromeda are falling toward each other. Triangulum here seems to have already interacted with the Andromeda galaxy. And so that's our local group. It's, so this is 1 million light years. So Andromeda is 2.5 million light years away. When you see it, if you look through a telescope or you figure out where to look with your eyes, we have skies dark enough in the Adirondacks, you can see it without a telescope if you have good eyes, or with binoculars. That light has been traveling across the universe for 2.5 million years. and whack, it hits you in the retina, and you say, oh look, the Andromeda Galaxy is visible today. Pretty amazing. All their friends, all the other photons, they fell on the ground. They didn't get to tell anybody what they left. So the ones that hit your eyeball are lucky. So when you do that, you're giving a gift to the galaxy by looking at it. Those photons, they're very happy to hit an eyeball. All right, so this is the local group. What if we zoom out from it? Wow, so here's the local group is a little puddle in here now. Oh, and look at this thing. The Virgo cluster. That's a pretty dense cluster of galaxies. These dots are galaxies. These are not stars. These are galaxies. And here, Eridanus cluster, the Fornax cluster, all these. And so we got clusters of galaxies. Now this distance is 10 million light years. All right, so across here, that's about 50, so this is about 1 billion light years going across here. Wow, it's getting big. And it's not like galaxies are evenly distributed, like the way that people would like it, a nice and even density. No, they're clustered. Well, that's weird. Here's an image. So this is done by Fernando Pena, who does a lot of work. It appeared as the Astronomy Picture of the Day on October 10, 2020. If you, my browsers, my web browsers, the home page, when I bring up the browser, it's always on the Astronomy Picture of the Day. And there are just amazing things going on. It's a nice way to learn a little astronomy every day. So this guy here is the galaxy M87, which has a black hole in the center that was imaged by, well, it wasn't imaged, but its near surroundings were imaged by the New Horizons Telescope, where they used radio antennas all over the Earth to create an antenna the size of Earth. But that's a different topic. But we've seen the black hole in here. So this is trillions of stars. This is probably trillions of stars. If the chance for life is 1 in a billion, hit the wrong one. If the chance for life is 1 in a billion and there are a trillion stars, it's happened 1,000 times. Wow. Yeah, every one of these smudges, this is a star. Right here, this is a star. All these smudges, these are galaxies. Hundreds of billions to trillions of stars. You can look at this and, who needs box wine? Just look at a picture and you get drunk. All right. I still like box wine, but I know. So let's zoom out farther. So now here, well, the local group, we can't even see it anymore. Here's the Virgo supercluster. And remember, that was 1 billion light years across. And there's all these others. Hercules supercluster, Capricornus supercluster, Pisces Cetus supercluster, the Columba supercluster, and here the Pisces Perseus supercluster. That's my personal favorite, because that's what my research group has been studying. And I'll show you why a few slides from now. So the universe is kind of lumpy. Well, why would it be lumpy? Okay, this is one of our puzzles. Not only did we learn from galaxies. Now in the galaxies, 90% of the mass of the galaxy is the dark matter. The stuff, the glowing stuff, normal matter, which we now call baryonic matter, because it's heavy, the root of bary. 10% of the galaxy is the stuff we know of as stuff. 90% of the galaxy is dark matter. We don't know what it is. So as astronomers, the more we learn, the less we know, is absolutely true. So, yeah, clusters of galaxies, hundreds to thousands of galaxies, also gravitationally bound by dark matter. In the 30s, a guy named Fritz Zwicky who was working at Caltech, he recognized that the galaxy clusters, he could see the speeds the galaxies were moving in the galaxy clusters. And there's not enough mass that we can account for by all the stars, you know, and you say, okay, this is 1 trillion solar masses, this is 1 trillion solar masses, this is 1 trillion solar masses. You add up all the mass, it's not enough to keep the galaxies. They should all be flying away. So he also said, no, we need some invisible matter to hold these things together. And these, see these warped images? Those are actually galaxies that are farther away than these, and the light passing through this cluster of galaxies has been bent as though it's a lens. It's called gravitational lensing. Einstein predicted that back when he came up with general relativity in the 19-teens. They were smart guys. All right, so clusters of clusters. All of these dots are now galaxies or clusters of galaxies. This, so the labels are on here, you can't really see them, but you can see it's lumpy. So here, way over here on this image, this thing, this is, now this map is the map of the sky as we see it from Earth. And the our galaxy is at a weird angle with respect to our sky. And so where our galaxy is a zone where we can't see any other galaxies. So this is the zone of avoidance. And it's just that the Milky Way is blocking our view of all the galaxies beyond it. And so here again is the Pisces-Perseus supercluster, which we used to say when we had Arecibo in Puerto Rico, we used to say it's a lizard. But now, well, now we're using one in West Virginia, so I guess it's a fox. So, or a dog. You know, you can almost see a skinny dog with tail up, barking, legs down here. All right. So, when we zoom out even further, all these galaxies, clusters of galaxies and clusters of galaxies, they all create what's been named Laniakea, immense heaven. Our home supercluster. It's been determined, and it was on the cover of Nature, this group from Hawaii, Brent Tully was one of them, they measured the galaxy speeds, how fast they're moving away from us. They measured their distances from us, and then they stuck all these in a supercomputer. And the supercomputer used Bayesian statistics, and it went through and it figured out a coherent three-dimensional model of their motions responding to gravity that would create the observed velocities and distances. So we're going to play a little video here, if we can click on the cover here. And so this is released by Nature. You can just Google, Laniakea Nature video, and you can find it. You can see Laniakea called immeasurable heaven or immense heaven, but since we measured all those galaxies, immeasurable doesn't really quite make sense. So I say immense. And so here is one of those images. And so yes, it's like a watershed of galaxies. And we're here in the Adirondacks, so yes, we're up in the head of the watershed. Isn't that perfectly right? All right, so that's where the Milky Way is. This, where it's reddish in here, that's the high density region of the Virgo supercluster. And over here, they call it Perseus Pisces, but they're wrong, because astronomers always go from west to east. So it's the Pisces-Perseus supercluster. They are going in alphabetical order. That doesn't work for astronomers. So these are some of the debates we have in our meetings. Yeah. All right, there's not time for those on Zoom. It's, all right. So this is what my group is studying. So here, these white lines, they show how the galaxies are falling toward the great attractor. Unfortunately, the great attractor is in the zone of avoidance. It's on the other side of the center of our galaxy. We can't see it. We know it's there because of the motions of all the other galaxies. So that's the next, that's one of the puzzles that people are working on too. And so here, the Milky Way, that's where we're sitting, high up in the valley. And so this is the supercluster that my group is observing and studying, hoping to get some more of these white lines for this one and find the great attractor for the Pisces-Perseus supercluster. So, we've got this great structure, but it's puzzling. Why is it lumpy? All right, so let's see if we can figure this out from the history of the universe. So, the universe is expanding. So it used to be smaller in the past. It was smaller when I started this talk than it is now. And it's expanding faster than the speed of light. So, the expansion rate gives the time of the beginning of the expansion. It's, so it's been a pretty steady expansion with a couple of bursts, but it's been expanding. We run the tape backward. It's been expanding for about 13.8 billion years ago. So at that time the expansion began. That's the beginning of time. Time and space are constructs of this universe. You can't ask what happened before the Big Bang because time didn't exist. And Stephen Hawking used to say that asking what happened before the Big Bang was asking what's north of the North Pole. It's just kind of a nonsensical question. So when the expansion began, the universe was filled with energy, but it was acting like a gas, and as a gas expands, it cools. And matter precipitated out of this energy. We see this happening. We can do it at CERN, all right, on the border of Switzerland and France, the big particle accelerator there. They can actually get particles to precipitate out of energy. And so gradually, in about the first 3 minutes, nuclei of hydrogen and helium had formed, but it was too hot for the electrons to get bound to them. So there weren't atoms yet. That took about 300,000 years of expansion before the universe was cool enough that the nuclei could capture the electrons. And when they did, the universe became transparent. So, atoms of light. Every atom, so here's helium, here's oxygen, here's neon. Every element absorbs and emits only certain frequencies of light. Most light goes right past atoms and it isn't absorbed. We walk around in an ocean of nitrogen and oxygen in the atmosphere, and light streams right through it. Because most light just isn't interacting with these. If you get dust in the atmosphere, then that blocks the light, but not the atoms. But light does interact with all charged particles. So, let's make a model. Here are nuclei and electrons. So there are nuclei, here are electrons. And so, when a light ray goes through, it's going to interact with every charged particle it sees. So, a photon coming in, it just goes from particle to particle. And so when you look into this universe, you see right next to your eye particle that the light last bounced off of. It's like when it's snowing, so you're up on one of the peaks. Now you're up on Marcy and you look over and you can see sunlight peak. But then it's, and why can you see it? Because so if this is the peak I'm looking at over here, the light hits the rocks and bounces toward my eyeballs. All the way across the valleys it's going rock, 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 whack. Hits me in the eyeball and say, oh yeah, that's a rocky peak. The fog rolls in. Now, that's a different photon. Because when it hits me in the eyeball, it disappears. So that photon is done. So another photon hits the rocks, and it's on its way, rock, smack, fog. Fog, smack, fog, smack, fog, smack. Finally, it gets to my eyeball, smack. Oh, it's foggy. Because that's all I could see. Because the last thing that light interacted with was a fog droplet. So, but when we don't have fog, we have atoms. So here are atoms, so all the electrons are bound to the nuclei. They should be around the nuclei, I know, but I'm taking artistic license here. And so now, the photons go by the atoms, they don't notice them. Bang! Ah! I can see to the other side of the universe. So here, the universe is opaque. Over here, the universe is transparent. The universe is transparent. So, when this happened, the universe was at a certain temperature and it was opaque. Opaque bodies have a certain curve. If we measure how bright they are in every color, every wavelength, or every frequency, it varies, and there's always a peak. There's one color where it emits more energy than any of the others. The wavelength of that peak tells us the temperature of that body. So, we discovered this radiation from the foggy universe. Penzias and Wilson in 1964 did this when they were trying to figure out the static in their microwave communications. I mean, they went so far as to clean pigeon poop out of the horn antenna they were using because they thought maybe it radiates in radio. How do we know? Well, no, it was the universe itself. It was this echo of the Big Bang, the radiation from the opaque universe that's still around. And it was supporting evidence of the Big Bang, not the Big Bang, sorry, I'll fix that. And it gives the temperature of the universe. And so we observe it. This is one of the latest observations. This is from, just a few years ago. The Planck, the curve is named for Planck. And so it was the Planck satellite set up to measure just this. And so you see this mottled egg here. Again, it's the whole sky in the reference frame of Earth. And so their bluest blues are slightly cooler than the reddest reds. The difference between the bluest blue and the reddest red is 1/1,000,000th of a degree. A Kelvin degree, but a Kelvin degree is the same size as a Celsius degree. So 1/1,000,000th of a Celsius degree difference. But it wasn't smooth. And it turns out that little tiny variation, 13.8 billion years ago, was enough to give us the lumpy universe we see today. So the hot spots, that indicates where there's a little more dark matter and the other matter is starting to fall in. And when you get collisions, you get heat. So that's why they're a little warmer. And these are a little cooler because stuff is leaving it. It's falling away. So we can use our computers now to run time forward from this event. So the Millennium simulation from Max Planck Institute in Germany took the cosmic microwave background, which is this image essentially, these data, add gravity and time, and let it evolve. Now the scale they have is 50 megaparsecs per age. That's 230 million light years. So that's good enough. And Z is a measure of time before now. Z equals 20 is the beginning of time. So let me go forward and let's see, how do I get this to work? Nope. Yeah, you got to click on it, Scott. So this is 230 million light years. So you notice this mottled, it's going to sharpen up because where it's brighter, that's where matter is falling in and it's getting even hotter. And where it's darker, there's nothing being attracted there, so it's getting less dense. And so this is where the galaxies and the clusters of galaxies are forming. This is the lumpiness emerging from our image of the cosmic background radiation. And I can't look at this and not see a neural network. I mean, it's just, you know, the universe is thinking. And so this is it. So here may be the great attractor. The Milky Way is out here on this, in this distant valley, and we're looking across over here at the Pisces-Perseus supercluster. Wow, what an image of the universe. And in really a century ago last year, they debated whether there were other galaxies. And now we know this. It's been an amazing century. What's the next one going to be? So, the next one, the illustrious simulation. So all of that, this was just dark matter. Oh, I can't go up there. That was just dark matter. No real matter. No, you know, gas and dust and stars. So the illustrious, the laser pointer and the forward, too close. So now we're going to add gravity and time and the physics of stars and galaxies. Now let's let this one evolve. So this is one for you. So this is a 32.6 million light year cube. Here's the dark matter evolving. Looks like the Millennium simulation. You see where the dark matter is getting denser. Over here you'll see gas starting to heat up as stars form. And so this is 1.5 billion years into it. 1.7, 1.8. 2 billion years it's taken to get this far. We're getting galaxies forming at these nodes. All right, 2.5 billion years. Now, as we go through, you'll see these things that seem to burst. Those bursts are taking hundreds of millions of years. That was hundreds of millions of years. That's the evolution of the galaxies that we astronomers can go out and look at other galaxies and see these processes, where they're going on, where they have happened in the past. Isn't that amazing? It's like, these are the true fireworks of the universe. Okay, sped up a little bit. All right, so now we're at 7 billion years since time began. And yeah, these bursts, we see these bubbles of stuff around galaxies. And it's just amazing. So we're up to 8.8 billion years. And space is getting filled with stuff. It started out as dark matter and hydrogen and helium, and now it's filled with all this stuff. Right? The explosions of stars created most of the elements we're made of. Something like 75% of the elements we're made of came from exploded stars. So now we're at 11. Right? Coming up to 12 billion years. And coming up to a universe that we recognize. Wow. So that is now how we see the history of the universe. So, this large-scale structure was created by this initial, not quite smooth distribution of dark matter. Galaxies, clusters, superclusters, these trace the distribution of dark matter. So when I'm studying the Pisces-Perseus supercluster, when I'm observing galaxies, but I'm looking for the dark matter, because the galaxies are the only way for us to see the dark matter. They're the tracers. You know, my friends in biology put molecules into, they put atoms into molecules that glow in the dark, so they can trace how a certain molecule goes through a biological system. For us, the galaxies are those molecules, the tracers. They're the only way we see the dark matter. What is it? We don't know. They're ideas. We're hunting. All right, we're hoping the next generation is smart enough to figure it out. Because we're trying to find it out. And it's a great question to be asking. New telescopes are being built. The CCAP Prime, these are both being built in Chile because the Atacama Desert in Chile is so high and dry. Less atmosphere for us to look through, and a lot less weather means a lot less corrosion on the instruments. So it's a great place to build telescopes. And so my research group includes some Cornell colleagues, and they have been two of the movers and drivers of the CCAP Prime. And then the Rubin Observatory, Vera Rubin Observatory, Vera Rubin was the one who figured out the dark matter in galaxies. And she was a young astronomer and a woman in the 60s. And, you know, putting forth this controversial idea that finally won the day. But unfortunately, she died before getting a Nobel Prize, and they don't give it posthumously. You know, some people's great discoveries do get overlooked by the Nobel Committee, and particularly when they're people of gender. Yeah, of a particular gender. So at least Vera has an observatory. All right, Hubble got a satellite observatory, but at least Vera's getting one now. And so my research group, some of us joined one of the science collaborations at the Vera Rubin Observatory. And what we're going to get from the observatory, when it starts running, it's going to be an automatic observation of the entire sky visible from its position every 3 days. And it's going to produce a terabyte of data per night. So there are huge science collaborations where these data will get processed at the observatory. And this is the work that's going on now, figuring all this out, because it's still being built. And we expect it to start operating, we are hoping, for October 2023. So my group is part of the preliminary work because we want information on a certain type of stellar explosion called a type 1 supernova that's very easy to measure the distance to, because they all are the same brightness. They're the same process, so they all come to the same maximum brightness. So if we can watch it brighten to a peak, we can figure out the distance to the galaxies, and that helps us figuring out our map of the Pisces-Perseus supercluster, which is going to be similar to the Laniakea one. And so there's still a lot of exciting stuff going on in astronomy. So what do we know? We don't know what dark matter is, but what do we know? We know the universe started expanding 13.8 billion years ago. It cooled with that expansion. Particles precipitated out of the energy, gravity gathered the particles into stars, the stars into galaxies, galaxies into clusters, and clusters into superclusters. And 4.5 billion years ago, the sun and Earth formed out of used star stuff that already had carbon, oxygen, nitrogen, calcium, iron. Life arose on Earth about 3.5 billion years ago. You know, Earth is barely cool enough for there to be a puddle and there's somebody swimming in it. Humans invented telescopes about 400 years ago. And now we observe the universe in visible, radio, infrared, ultraviolet, X-rays, gamma rays, and even gravity waves. Humans invented computers less than 100 years ago. And computers can now show us the history of the universe and help we astronomers figure out what we need to observe. So, as I always say, the adventure continues!